Welcome everyone. My name is Davide De Biasio, and I'm a member of the ISQG Outreach Activity team. Today, I will have the pleasure of interviewing Professor Laurent Freidel. I hope I pronounced that correctly or appropriately.
Yeah, Laurent Freidel, yeah.
First of all, thank you very much for having accepted our invitation. It's a real honor for me to be here today. If I understand correctly, you started, and I remark this because most of our audience will be comprised of PhD, master, bachelor students. You started your career as a PhD student at the École Normale in Lyon. Is that correct?
That's correct, yes.
Perfect. You're currently a research fellow at a faculty member at Perimeter Institute in Canada, right?
Yes, that's correct.
Perfect.
I'm also the faculty chair at Perimeter currently.
Perfect. So physics-wise, going to the topic, you have worked on a remarkable lot of issues related to quantum gravity. As a young PhD student, I'm personally amazed by your Google Scholar page, and it's something I want to stress. But concerning this, would you like to say something more about your research interests? Present yourself and tell our audience who you are, what you work on.
Okay, yeah, no, I can try. On the one hand, my research interest is very simple. It's quantum gravity. and by that, I mean, this is my entire focus. And I want to do whatever I can to make that concept, that thing that we call quantum gravity happen. And now, as you mentioned, if I go through the history of what I've been, so I did my PhD. I didn't do my PhD was more mathematical physics, and then integrable systems, and then topological quantum field theory, and then I slowly evolved toward more quantum gravity interest. But as you mentioned, I think to master quantum gravity, and maybe I'm part of a generation that when I did my PhD, all the fields of physics were still in the same room. I think today, if you're a PhD physics, might be hard. So when the first school I went to, Les Ouches School, well, I could have a lecture of condensed matter, or, I could have a lecture on non-commutative geometry by Alain Cohen, or on string by Polyakov, or on Toft on black hole and information. So, I'm still part of this maybe old generation, old enough to be in a generation where I was trained and it was all of the same. Right. And then, of course, it kind of grew out. There's a lot of information out of there. But so with that focus in quantum gravity, I've tried to bring in, many different fields. So I worked in, quantum field theory, CFT, topological quantum field theory, so more like deeper aspect of quantum field theory. I worked on strong gravity wave, understanding that, because I think, if you want to understand the quantum nature, part of my research is also a lesson of humility, going back to the basics. What do we understand or we do not understand before we jump ahead? And then I worked on, loop gravity, spin forms, so really kind of trying to go deep, hardcore on the other side of the world, where you just focus on try to picture what quantum geometry is. And more generally, I like foundations of quantum mechanics, I think is important. And I have interest in some papers on philosophy and history of science, because if you want to be part of a new discovery, it's kind of interesting to understand how these previous discovery were made, and ultimately, I think at some point any discovery should be linked with phenomenology. So I've been trying to think about through maybe this, infrared UV mixing, or what we call relative locality. What could be the weirdest or the most radical aspects of a theory of quantum gravity, even without having one. So so it's very simple. I'm very focused. There's only one thing I want to do. I don't want to be and I'm not dogmatic. I've learned a lot of subjects for that focus. I hope that answers.
Thank you very much. What you said really resonates with the aim of the society I am glad to be part of, because the ISQG aims at bringing people working on quantum gravity from different approaches with different methods, bringing in different stuff in the same room, as you said, because it is clear people now do not fit into the same room, but at least people working on quantum gravity should try to talk to each other. So we perfectly agree on this point, and we perfectly agree on the importance of philosophy and foundations. But we are here to discuss quantum gravity. So I will start, being this the first interview of our series, the responsibility of setting the stage for the others bears on our shoulders. So I will ask you, what is quantum gravity? Why do we need it? Should gravity be quantized in the first place? What does this whole thing mean?
Okay, well, that's a lot of question.
Yes, a lifelong one.
Yeah, let me try to simple. So what is quantum gravity? The simplest answer is that we don't know, and that's why I have a job.
Sure.
Now you could say, it is, historically, it is a project. It's a quest, which have been going on since almost right after the invention of quantum mechanics and general relativity. That question was asked, right? So it's a quest that has been lasted for 100 years. It's a beautiful quest, very frustrating quest. It's a quest that many people have claimed over the years that they have found the answer to it, and then not. But so it is, for me, it's one of the most ambitious and fascinating quests that the human mind can try. Maybe we can talk about understanding the brain, or understanding what consciousness is, which maybe is after. But this kind of quest, which is absolutely out there, and as any quest, which is really extremely challenging, trying to make sense of what are the questions you want to understand, right? Because in any research project, it's half or more than half of the understanding is really what are really the questions that we want to settle down, and then what are the techniques, what are the new objects that we have to invent to master these techniques. So often these objects have applications all over physics, and quantum gravity, or the history of quantum gravity, is filled with such examples, like the descriptions of the Hamiltonian system, or the constraint system that is used for gauge theory, the concepts of ghost, or recently the concept of development in entanglement entropy. It's kind of it's endless, or as we're going to talk, maybe the concept of memory effects and stuff like that. So sometimes having, trying to rub yourself against a very, very hard problem brings a discipline, a simplicity, a humility, and brings new discovery. But I don't know yet what quantum gravity is.
So let me briefly end now, because I want to be sure that everyone is on the same pace. So I will forget all I know, which is not much about quantum gravity, even though I'm doing my PhD in the topic. I'll be the street man asking questions. So we have a known quantum theory of gravity, general relativity, right? It's a relativistic theory. It works well in the solar system, has its problems. We all know that, black hole stuff, cosmology, and all of that. We used to have known quantum theories, for instance, of electrodynamics, right? And we managed to quantize those, to make them into quantum theories. Why is it so hard to quantize gravity, to turn gravity into a quantum theory? Because that's the point, right? Construct a theory of gravity that works roughly on the very small scales or high energies. Let me state it like that. I know it's a bit imprecise, but
sorry. I should have explained it. So what do we expect quantum gravity to be? As you're saying, we have a profound understanding of the physics of what we call the ultraviolet. I'm going to say maybe the UV, which is the small scale physics. And we have a profound understanding of the large scale physics, which is gravity. And for some reason, physics has this property that when you go to extremely small scale, or when you go to extremely large scale cosmology, it becomes extremely simple, right? All the complexity in nature appears at our scale. We are like the mean square root between these two scales, and then we have brains, we have complexity, we have chaos, we have all of that. But when we go into these two extremes, we have we are very simple. I mean, okay, it's mathematically complex, but in some sense, when I say simple, it means that, you know, with a computer, with a pen and pencil, with study, I can really kind of understand the nature of these objects, even without experiencing them. Like one of the most radical example for the biggest one was Einstein predicted that black hole, you know, would exist, and then they would eventually merge and they would emit gravity wave. And then, okay, it took after 100 years, a few years ago, we saw that. And we saw an event that is, you know, 5 billion years away. We will never be there in an environment where we cannot survive, but we could predict exactly what would happen, which is kind of amazing, right? That's the amazing property of. So, okay, so we have an understanding of quantum mechanics and quantum gravity. So gravity, what it tells you is that somehow it brings something new to the game. Both of them bring something new to the game, but it brings gravity brings what brings new to the game is the fact that the main notion of geometry, the main notion of space and time, which is really the place where we put objects and we do within, you know, we do physics within space and time, is itself dynamical. And that, to some extent, we know how to, you know, manage. But you know, the goal or the prospect of quantum gravity, in some sense, is to understand what is the quantum nature of space-time. So think about the discovery of quantum mechanics in the beginning of the century. You know, one of the discovery was Einstein's, for instance, Brownian motion discovery, right? You look at a liquid and then you had the evidence that, no, it's made of constituent molecules. Right, that's what quantum mechanics does. It has this tendency to create quanta, which means discrete objects that are constituents. And then we realized that, you know, nature is made of constituents. The sky is blue because it's made of constituents, and the water boils because it's made of constituents. So, in fact, we were witnessing quantum mechanics for thousands of years. We didn't know that it was quantum mechanics, right? So, quantum gravity, you could say, is really the prospect of trying to understand, you know, what are the atoms of space and the atoms of time? What are the fundamental constituents of nature? And why is it hard? Because the way we understand physics is that first we set up the theater, and the theater is space and time. Space and time is given, it's God-given, it is kind of fixed, or maybe it's a little bit moving. And then on it, we can define fields and objects that move on it. So it would be as like, you know, you have a play and you have a theater. The theater is fixed and the play is fluid, right? But now imagine trying to understand a play where the theater itself is part of the play, and the floor and the ceiling. And so where do you start, and what do you keep, and what do you, you know, and that explains, and in fact, these questions, where do you start, there's different perspective, and that explains maybe like there's 2 or 3 big entrance perspective onto the problem. Does that?
I think that sums it up pretty well. If I may make a synthesis, then tell me if you agree. On one hand, we have general relativity that tells us how space-time behaves, at least on large scales. So we have black holes, as I said, cosmology, as you said, gravitational waves, and so on and so forth. On the other hand, we have quantum mechanics, or quantum field theory, as you like, which is more or less the framework in which all other portions of physics are written, right? It's, in a sense, the language in which we write theories. Dynamical spacetime, non-quantum, quantum theory, no dynamical spacetime. We have to find a way to write down quantum mechanical systems in which the spacetime itself is part of the system, it is dynamical, it is a physical degree of freedom, it interacts with other objects, and so on and so forth. Would you agree with that description?
Yes, I would agree with that.
Perfect. So
maybe we are putting under silence how weird quantum mechanics is, or how beautifully it is.
Yes.
How beautiful it is. But yeah,
it's other old topic, and it's super complicated. I would be more than glad to discuss that together, but I would now try to bring our conversation to topics which are more close to your research, right? This is supposed to be the core of our
maybe you were asking why gravity should be quantized. Did we address that?
Yeah, I mean, if you want to get into that, I would be more than happy to listen to your opinion. Yes, sure.
Because I mean, you know, it's always a fair question, right? Is it, if you're a student, is it a valid endeavor, you know, to go through? And I think it's a very difficult question. And a lot of people would answer, and you just have to accept that they would say maybe not. That is, we have a framework which is quantum field theory. We have a belief system, which is a decoupling between UV and infrared. So we talked about the UV, the ultraviolet, the small and the big. And if you believe that, you know, and that's the current, if you think about the current state of mind of 99% of physicists, they believe in this concept of effective field theory, which assume this decoupling. And if this decoupling is true, so under this, it's very important to appreciate that when you answer a question like that, it always comes with a theoretical bias.
Okay.
Right. And often in quantum gravity, people have very strong opinion, but they don't tell you on what these opinions are, what hypotheses they use to be so decisive. So here I'm just framing. If you have this belief that effective field theory is really all there is, and there's the decoupling between UV and infrared, then in some sense, as we just said, the quantum nature of gravity is going to be one of the most, is going to be smaller than the smaller scale of particles, right? So it's something very, it has to be something very much in the UV. Yeah, you wanted to.
So if I may, this, as we might call it, this naive effective field theory perspective, because what is more or less the following. Physics changes when we go towards smaller scales, and as long as we stay at a given scale of length or of energy, as you said in the beginning, higher energies mean like smaller scales. We can, in a sense, neglect what happens at higher energies or at smaller scales. This is the traditional perspective offered by effective field theories, right? This is the decoupling between UV and IR you were referring to, right?
Exactly. And to some extent, it works. Like, you know, if you study biological system, you don't need to know how cosmology functions.
Yes.
Right. So that's kind of,
yes.
So it's a very robust and solid, you know, I don't know, picture. And of course, it's supported by these technical developments of the renormalization group. So in physics, we call it the Wilsonian picture of decoupling. Now, if you believe this picture and you think this is the fundamental picture of theory, then I would say, well, no, we don't need to quantize gravity. Or in some sense, we already have a framework to quantize it, which is effective field theory, that is given a certain level of precision. Quantum gravity is only going to be something extremely ultraviolet, something that appears only at very, very, very small scale. And for all practical purpose, I will never be able to maybe witness it.
Yes, sure.
Right?
Sure.
So, yeah, so that's why a lot of people would say that we should not go there. I mean, at least when I grew up, you know, maybe now the picture has changed, but, you know, I was the first person doing quantum gravity in my, I want to say my continent or something like that. Now it's much more common, but
if I may, just to give some kind of reference to people listening to us, when you mention small scales at which quantum gravity should become relevant or significant or witnessable or whatever, you are really referring to scales which are much, much smaller, because people might not be, and not in the field might not picture this, much, much smaller than atomic or nuclei scales. Actually, smaller, well, it's a matter of proportions, right? We are more or less meter scales, 10 to the 0 scales, and nuclei, I think, I'm really bad with this, but 10 to the minus 18 meters scales, right? While quantum gravity is expected to become relevant in this picture at 10 to the minus 35 meters, right? Is that correct? That's supposed to be Planck's length. So that's really much, 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 much smaller than billions and billions of times smaller than nuclei scale. So that's a very small scale. So you should, in principle, not expect that to be relevant for our everyday physics life, at least at the scales which we can explore nature. But I guess you're saying that's not the case, right?
Well, I mean, yeah, no, I want, yeah, for me, you know, gravity should be quantized, just, but Yeah, no, exactly. I mean, let's say it's still a possibility that this is true. That is, if you work in quantum gravity, you have to have the rigor to assume that you're making a very strong hypothesis, and this is why. I mean, I personally believe quantum gravity is an absolute breakthrough, because the only the reason is going to be important is because it kind of failed this strong hypothesis of decoupling of scale. And if I think like that, I mean. I started by saying, oh, it's about quantizing the atom of space-time. You see, one of the strong implications it needs to have is also this connection, which is completely mysterious, whether philosophically or technically, between UV and IR. And personally, I think the source of tremendous new observable. I'm not saying I'm right, but I think this is what a breakthrough kind of look like. And we say we have evidence that somehow the picture is not as simple, because we know that gravity is also about black holes. So we know that this nice picture of decoupling, that the higher you put the energy into a system, the smaller you go. At some point, it doesn't work with gravity, because if you try to put so much energy, somehow what's going to happen is exactly the inverse. You're going to get a bigger and a bigger and a bigger and a bigger object, which is a black hole. And big black hole will behave quantum mechanically. So there's already some very interesting tension between a set of belief that people hold very, very dear and another sets of evidence. And I think we just have to be, as intellectual, we have to be honest. Like when there's fundamental paradox in the game, and physicists often hold these two beliefs together. But being a quantum gravitist means, okay, if you hold two beliefs together or two conceptual systems, and you don't acknowledge that they're in deep conflict, I think you're dishonest. So this is why we have to do gravity. It's just at some point we have to resolve this fundamental tension. This is more an intellectual reason, I would say.
I think what you're saying is crucial. So let me make it a bit concrete with an example, right? We use, for people listening to us, we typically use particle accelerators, right, to investigate small scales. And at our stage, putting more energy into particles, as you said, means resolving, that's the word physicists typically use, smaller and smaller and smaller scales. But if we take, and this is quantum field theory, quantum mechanics taken at face value, but if we also take general relativity at face value, at some point, by keeping, putting energy into a particle in an accelerator, we should start producing black holes, because we have a dense enough energy distribution so that black holes are produced and stuff like that. So, but when you keep pouring energy into black holes, they grow, right? They grow. So this means that you decrease your scale, decrease, and then you start increasing it again. You have this kind of rebound in one that hints perhaps at the existence of a minimal scale and stuff like that. And this is really crucial because it defies all our intuitions, right?
Yes, exactly. No, that you said it well, and then it points towards something. So this what we call this Heisenberg microscope, which is the fundamental discovery of quantum mechanics, right? That energy is connected to wavelength, and this is where this constant h bar appear, right? And is inversely, and wavelength is the resolution. And that's a law of nature, and at some point this law of nature get inverted, and that's for instance that explains one type of ways where there are people who are thinking in depth. You can think, I would put them in non-commutative geometry. For me, this is relative locality. Even before, how is there, what kind of conceptual framework could make sense of that? And I think it's one of the very important questions of quantum gravity. There's a few, 2 or 3 like that if you give me a theory of quantum gravity, they would have to resolve. So that's one that has to be addressed. Yeah.
There was a small technical problem, but we are back. It came at the right time because I was just about to bring back the question I tried to pose previously. Namely, I wanted to ask you something about one of your big research interests, if I can call it that way, namely symmetries and their interplay with boundary charges, boundary degrees of freedoms, freedom, local holography, edge modes, which are, and there's a lot of terminology involved. So I think it's important, first of all, to make it clear for people listening to us and then to get into the topic. So if you want to take the stage, I will be more than glad to learn something about this from you.
Okay, thank you. So yeah, it's true that in the past, whatever, 7 years, I came across this idea. Let's call it. So it's the central concept, and I'm going to explain a little bit, is the concept of corner symmetry and local holography. And I think it provides kind of a form of new paradigm that unifies certain key ideas. So let me try, before I explain what it is, let me just try in what way what I'm doing is kind of completely different from the strategies that were done before. So I would say up to this program, most of the approach of quantum gravity were what we call top-down, right? Top-down, people mean, you know, physicists means that you have an idea what is the fundamental constituent of nature. For instance, it's a string theory, and you need to quantize the string, and then you need to work very hard to connect to the real world that is us, right?
So, if I may, using your terminology or the terminology we used before, you start from the deep ultraviolet for the super small scales and then move towards a word.
Exactly. And that approach had been very successful. You could say for Einstein, he postulated, you know, the Einstein's equation independent almost of any phenomenology. I mean, going way beyond the phenomenology. Or particle physics, when the problem was we wanted to classify nucleon, people postulated, no, it has to be the Young-Mills model, you know, like a fundamental QFT, etc., that explains all the spectra of hadrons, okay? Instead of you trying to go through the complexity. So, you know, I would say since the 60s and 70s, or even, this is really the approach, right? And then, of course, as we're saying, you know, this means really, and you can say there's maybe 3 main perspectives there that have kind of survived, and you can clump yourself into one of them on some broad set. So string theory is one idea where you postulate, string theory is interesting. The fundamental postulate of string theory is that you want to look at the symmetry property of the smallest probes, which is called conformal invariance, and then you deduce Einstein equations from that. It's kind of radical. You say, I deduce Einstein equation from, which is the biggest equation that govern the universe, from the property of the smallest object. And it's, you know, that's one perspective. Another perspective is you know, which grew up is, I would say, the one implemented around loop quantum gravity. Is, as we were just saying, you know, if you try to do gravity, there's something that at some point tells you there's a special scale, the scale where your Heisenberg microscope rebounds. Instead of, you put more energy, instead of zooming in, you zoom out, okay? It means like there's a fundamental length scale, we call it the Planck length. There's a fundamental energy, there's a fundamental temperature that you cannot break through. And if you think in terms of Planck length, then you might think, well, maybe it means that the world is atomic, right? There's some fundamentally discrete structure that explains this object. So there's, you know, when I say loop gravity, there's also causal sets, or a lot of people there, you know, there's a myriad of different models where people have postulated. Here, I postulate that the fundamental geometry is discrete. Loop gravity is kind of, in some sense, more interesting because it postulates some amount of discreteness, but it also gets some amount of discreteness through quantization, like the area quantization. Yes. So, which is interesting. In some sense, this is where you would like to go. You would say, like to go, it's not that the space-time is discrete. It's somehow it's quantum mechanics that make it look like.
Yeah, it should be some kind of result of the theory, right?
It should be a result of the theory. And I would say LQG, look, quantum gravity, as we say, as part of that, and not fully, but I think, and it has one key element there, which is that the notion of geometrical objects that we use it like computation of the area of an element is now an operator.
Yes.
Okay. Instead of being something God-given, classical, it's an operator.
If I may, just
that's one of them. Yeah.
To connect to what we said before, in a sense, string theory postulates some kind of new degrees of freedom in the deep UV, like the string and its excitations, while loop quantum gravity tries to adapt the way we quantize things to a dynamical spacetime, right? That's what you said before. We typically postulate spacetime, while here we try to quantize in a way which is consistent with having dynamical spacetime. Is this correct?
So it's quantized geometry versus string theory says maybe geometry, philosophically is very different. Maybe geometry only exists through the probes I send in.
Yes,
The
yes.
particle part, right? Is geometry something that exists on its own? So then you're a gravitational person, or if you're a particle physicist, no, the only thing that exists are particles. So you can, and both are true, okay? But this creates big camps if you want to choose. In some sense, this is one of the tension of GR, which is very important.
And then they branch, right? So things get even.
Yeah, and then they branch. But I would say, okay, there's this kind of let's say, at the core of it. And then, of course, what happens for every theory, and there's a third one, is that there's a core idea which is profoundly true. And then people build up, long list that deviate. And then you have this very rigid edifice that prevents people, they create silos, I would say, of the mind, right? So this is, when I'm talking about my approach, it's one where I'm going to bring down the walls of these silos, going back to, so this approach I'm describing is not a top-down approach, it's a bottom-up approach. It's like trying to understand really precisely what is the nature of quantum and gravity in a regime that I really control, and learn from that and create a framework where any theory of quantum gravity will have to submit to the discoveries that I'm going to discuss about. Okay, so then we can agree on that, and then we can find a common ground. I would say there's a third element which is very important in my program, which is holography. Okay, so it is this idea, and this is the one that I'm going to maybe expand more on. In fact, it's an idea that it's presented as a new idea, but it's already something that was discovered in 1915. It goes back to the theorem of Noether. Noether, which is, wrote a remarkable paper in the 1910s at the instigation of Hilbert and Klein to try to understand the nature of gravity. And there she kind of showed something kind of remarkable, is that if you have a gravitational system and that system has a boundary, so for anything non-gravitational, we know that the energy is additive in the bulk, right? So the number of quanta in the bulk, the bigger the object, the more energy you have. But Noether proved that the energy, which is the fundamental concept in gravity that generates time evolution, that organizes everything, this is in fact a boundary observable.
Yes.
And that was discovered 100 years ago, but somehow it's so against the way we understand quantum field theory that it was kind of never acted upon. And this entire program called the corner symmetry program is just engaging with, front end with that result, which is this holography result, which is in fact true for any finite region, right? So this is what I'm doing. There is a top-down approach of holography, which is called ADS-CFT, where people postulate that the only thing that exists is ADS space, and the only thing that ADS space exists is at the boundary is a CFT, and it's super Young-Mills, and etc. It comes attached, and this is it. This is a top-down approach, and then it's you need to take it as a definition of quantum gravity. So these are, like I would say, the three top-down approach. And me,
if I may, because
I'm trying to set up the framework here.
Yes, and that's really important. So I thank you. You mentioned ADS-CFT. Here, this idea of holography, just to make it a bit clear for people listening to us, is the idea, an idea about the existence of some kind of correspondence between a gravity theory living inside some volume. That's what we mean when we say bulk. You said it before. And another theory without gravity living on the surface, the boundary of such volume, right? Yes. And top-down approach, as you said, you just take the theory on the boundary and use it as a definition of your corresponding gravity theory in the bulk, inside the volume. What you're saying here is that you are using holography in a way which is not this, right?
Exactly. So maybe, yeah, this is why maybe I'm trying to find the proper term, because holography has been used a lot. So I call it either local holography or, I mean, it turns out that the term that's becoming popular now is the term of corner symmetry, and I'm going to explain. Because the key concept is the concept of symmetry of nature, and yeah.
So maybe we can get
now to go back with holography, I didn't say philosophically it's a third. Often people misrepresent it as being part of string theory, but it's very conceptually different. With string theory, we say what it was. Holography, it's a very different conceptual starting point, as you're saying, that somehow a theory on the boundary determines the theory on the bulk. And it focuses on one key aspect of quantum gravity. As we say, every one of these programs, has to addresses one of the central questions of quantum gravity. And of course, the full quantum gravity needs to address all of three in some sense, okay? And if you just put, what is the word for,
yes,
guideline where you refuse to look at the other one, then, okay, then you're good in your work. But the one of holography, which is very important, is this property that we understand now, that somehow it seems that black holes, and in fact, maybe more generally, it seems like space-time region can be assigned a notion of entropy. Entropy is a thermodynamical concept related to heat, but it's also related to counting the number of degrees of freedom. Mm-hmm. And as I was saying, we used to the fact that the number of degrees of freedom in a box is proportional to the volume of the box.
Yes.
Right? But in gravity, it seems, and we have many, when you say evidence, like indirect evidence, semi-classical, that somehow a theory of quantum gravity need to explain why it's not proportional to the volume of the box, but to the area of that box.
Yes. Right? Pardon, let me stress this and jump in. Like when you study black hole physics, like in very simple terms, when you study black hole physics and you discover they seem to be thermodynamical objects like gases or other weird systems. We study with many components, which is something absolutely novel with respect to what we knew in general relativity. When you put a little bit of quantum mechanics in there, when you try to count the number of small microscopic degrees of freedom composing this big object, thermodynamical object, as you would count the number of water molecules, water glass or air molecules in this room, you discover they are proportional to the area, not to the volume of the black hole. And this is weird, right?
Yes, this is good. So let's say if you're interested in quantum gravity, you want to solve quantum gravity, we mentioned three fundamental problems that you have to put together. This fundamental inversion of the microscope, the fact that matters excite geometry, so quantum matter is somehow dual to quantum geometry, which is the kind of the string, and then the fact that geometrical objects are quantum, that's the fourth element, and then now the fact that entropy is holographic, or that gravity is holographic in some sense. Okay, and then and it begs it begs the question, like if you think about putting these things together, you start to get a feel even before doing quantum gravity, how radical and completely conceptually mind-boggling, this discovery is going to be. So let's go towards this program. So for me, it all started, and I have to grant some early collaborators like Alessandro Perez or William Donnelly, but it's especially work with William that changed. So we started to ask a very simple question. I've been obsessed with this idea that counting degrees of freedom, and why is it proportional to the area? But clearly, if it's proportional to the area, it means that it's important to understand what happens when you have a field theory or a quantum system and you cut it and you decompose it into a system which is inside and a system which is outside.
Yes. So when you introduce a surface, for example, in this room, right?
This surface, exactly. And now, so the surface is the two-dimensional, and so it's a boundary of a space, right? But it's also we call it a corner because if you draw it in space-time, there's two dimensions. It's codimension 2, which means that it's the boundary in time and in space.
Yes.
Okay, so it's very important to distinguish. I'm not talking about boundary condition. I'm talking about corner, entangling surface, separation surface between the inside and the outside of a system.
Yes.
And I wish I could draw a little causal diamond, that somehow. Anyway, so that's it's very simple, and it comes from a very simple idea. What is the project of quantum gravity? So understand. I go back, understand what are the atoms of space-time. Okay, maybe it's not atomic, maybe it's a fluid. Maybe what are the constituents? Whatever is you. I don't want to preclude, but what we would do in if I want to understand it, what is this chalk made of? Well, I would do something very simple. I would break it open and look inside.
Yes, sure.
And so this is what we started to do. We just started to do, okay, why don't we take a gravitational system and then decompose it into subsystem and see what you have to do, right? And for some reason, that was never really done fully or properly. It's a very simple question. And it's because in the language of quantum field theory, there's often this belief, or at least maybe it's technical, like the theory we know how to define or quantize, they're defined on the entirety of the space-time. It's all of ADS, or it's all of flat space, and all the observable are at infinity.
Yes.
So there was something preventing people from just asking this simple question. So we just look at that, and we try to understand what it means to decompose a gravitational system into subsystems. And what it would take to first cut the subsystem out, separate it, and then glue it back.
Okay.
Right?
Okay.
Because if you can glue it back, it means you have not lost, and you can cut a system and destroy everything, like put a mirror, but then you have a different system. So we want to okay. That was the idea. And what we realize is that when you do that, this process is controlled by the notion of symmetry, and that kind of changed the picture. So maybe this is a bit technical. So the fundamental theory of nature, and I would say there's like the two most fascinating theory of nature are first gravity, and the second one is QCD. And I would say, in order of if you're a theoretical physicist, there's two graal of physics. One is to quantize gravity, and maybe just nearby is to prove confinement. Okay. And these two theories, what they have in common.
Pardon me,
yes.
Just for people that do not know, QCD is quantum chromodynamics. Is the theory we use to explain nuclei, atomic nuclei, and together with a lot of other stuff, but in general, how nucleons like protons and neutrons are made, and confinement, like you have these fundamental degrees of freedom, fundamental objects we call quarks, and they seem to be bound into protons, neutrons, stuff like that. Confinement is the process that supposedly, I mean, we have a lot of evidence for confinement. For instance, the fact that we are made of protons and we do not, decay into quark, gluon, plasma stuff. But these objects are confined into protons. You cannot take them out, right? Mm-hmm. And we do not really have a full-fledged proof of this process inside our theory. So that's one of the holy grails of theoretical physics, right? Mathematically proving in a rigorous way, not only with computer simulations or evidence or, lattice computation and stuff like that, that there should be confinement in the first place, right?
Yeah. And so these two theories, they are what we call gauge theories. What does that mean? It means that in order to describe them as local objects, we need to seemingly add degrees of freedom or objects that seems to be relevant, and then we need to take them away into every other observable. It looks like we have a redundancy of this description, and I don't want to enter too much into this philosophical debate, but it's a debate that it's a profound debate that so for 100 years people thought that gauge symmetry is just redundancy. That is just, it doesn't mean anything, right? And there's another camp, let's say this would be like more particle physics camp versus the loop gravity camp that says, no, it's something fundamental. It's something that is about background independence. And so is it, and it kind of frame, if you think about quantum gravity, you have to kind of, position yourself. Is it really fundamental, or is it just some fluke and some redundancy, right? And so in this paper with William, we proved that, in fact, it is, in some sense, it's a little bit of both, but in a very precise sense. It means that if you have a closed system, it's gauge symmetry is pure redundancy. But when you start to cut it open, you find and you discover that now these gauge symmetries, which are redundancy, becomes true symmetry of nature. That is, they carry charges, they carry representation, they carry degree of freedom. And this is where the lingo comes. So the symmetry, we call it this corner symmetry. when you have a group of symmetry, group of symmetries, you transform your system and it looks the same, but it's different. Like a particle moving in that direction is clearly different than a particle moving in that direction. But there's a rotation, there's a similarity between these two motions. When I understand that motion and I rotate, I understand that motion. But they are different, right? They are mapped onto another, but they are different. They are not the same object. So this is a symmetry. At the why do I care about symmetry? Because in theoretical physics, any physical system that we know how to quantize, we know how to quantize because it has enough symmetry. So as somebody that has the prospect to quantize gravity, if I'm honest, my only and quantize gravity non-perturbatively, the only option is that system has enough symmetry for me to control its quantization finely enough. Okay.
If I can jump in here just to make things a bit more, more clear. You use two different words, symmetry and redundancy. And in very rough terms, when you use the word symmetry, you mean transformations that leave nature or laws of physics invariant, in a sense, like rotations. And, a ball is symmetric under rotations. You cannot tell if someone rotated it or not. Redundancies are, in a sense, transformations you can apply to your mathematical models without changing anything, but they seem to be different, at least on a philosophical regardless of the mathematics.
They are very different, and I think part of the work that I've been doing is clarify, and they were confused for many years. So part of the reason why we had some difficulty with quantum gravity is to confuse one with the other. Right? Redundancy, as you're saying, is extra bells and whistles you put in your mathematical description that you put because you like them, but you can do as well without them, right? And it's a more personal, aesthetical, whatever convenience. But symmetries are, remember, one of the problems is to count the number of degrees of freedom, count how many atoms there is in a portion of space. So when I say a particle here is different than a particle here, so if I have two particles there, they're related by symmetry, but I really have two states, not one. Right? If I have a particle plus a redundant description, I still have only one particle, right? So at the end of the day, it really matters for how do I count, what are the fundamental constituents, if you want. Okay. So first we discover this corner symmetry group that appears, when you decompose subsystems. And then this is where come the study of this corner symmetry group here. Now, when you have a notion of symmetry at the quantum level, you need to, what we call in physics, you need to represent that symmetry. Now, this is a very abstract notion, but it means, I can have the notion of the rotation, but I can rotate a vector, or I can rotate a plane, or I can rotate different objects where they have it's kind of the same action in the background, but they can be represented in different manner.
Okay, for instance, let's take a simpler symmetry, like a reflection symmetry, right? Objects which are symmetric with respect to an axis. You can have a snowflake or an apple or many different objects which are symmetric with myself, approximately. And these are different representations of the same symmetry. I mean, I can act with reflections on myself, on a snowflake, on a piece of paper, on an apple, and all of them will be symmetric. All of us will be symmetric, but those would be different representations, right? In a sense.
Very good, exactly. And then if you're a mathematical physicist, we have tools. If I give you a symmetry group, I can try to classify, give you a complete list of all the possible representations. Okay. Yes. And then I know if I have a symmetry for physical system that my physical system is a particular representation. And then from that perspective, all I have to tell you is what representation. And somehow if there is enough symmetry, the system is, I can do that at the classical level, but it's almost then easy to go quantum. Okay. So that's the power of symmetry. And as I say, I did my PhD. It's interesting, maybe for graduates, a little lesson, you see, is that whatever you learn in physics is never lost. Like I started, and one reason I was able to do that, I could grab this idea, I would say, is because I worked several years in integrable systems, where there you want to quantize a system, and you don't quantize the system, you quantize the symmetry, and then find the quantum system by representation. The symmetry is extremely powerful, extremely powerful. And if you were trying to quantize the system without that, you would get completely lost, right? So, and then so all this work I did maybe 30 years after came back to me as very useful teaching. And
never
it's always
throw away anything. Never throw away anything.
No, it will come back. You have to be here long enough. Keep an open mind. It's going to come back. Anyway, so we have this symmetry, we have this representation. So for me, and we're still talking about something very elementary. I'm talking about the nature of classical GR, understanding what we call the phase space. So there's a way to understand this object where you don't need to jump to a top-down approach, okay? There's a way, and then, okay, so then when we discovered that, we had to develop all the mathematical framework around, because it's subtle, and that's what you're saying. There's a lot of paper technical, but in some sense, it's more, okay, make sure that we have all the right technical tool. But what's important is we went from a point of view where gravity has no symmetry to the point of view where gravity has now infinite dimensional group of symmetries. A little bit like when people discovered that the theory of continuum phase transition in 2D was governed by an infinite dimensional group called the conformal symmetry group. Here we're saying, well, it's like that for gravity. So for sure, as soon as you realize that, that's what I'm devoting, I want to understand the nature of the symmetry, the quantization. And as I'm saying, any theory of gravity need to submit to that. If not to tell me, like, for instance, there was a proposal called Ojava gravity that said I could quantize gravity if I break all the symmetries. I mean, Lorentz symmetry. That's another option. You could say, even if you tell me, look, I break all the symmetry, that's not going to be my choice. But you do have to, submit to that. So I hope that explains some of the ideas. And now, what are the kind of results you can get there? And I emphasize it's a bottom-up approach, right? We are not the first beautiful result I find for me, and is very satisfactory, is that it gives me a complete conceptual framework where I can bring the core idea of loop quantum gravity and the core idea of holography, and they merge seamlessly. Okay, and by core idea, I mean maybe you have to throw away some aspects of loop gravity that don't belong, and I have to throw away some aspect of holography that, don't really belong to the theory of quantum gravity. But that's the first sign for me that you're on the right way, because as you're saying, there's different approach of quantum gravity, but breakthrough or discovery is not just concatenation of different perspectives. It's when these perspectives they fuse.
They merge, yes. Yes.
Right, they merge, okay?
Can I ask you to expand a bit on this? Like, when you say you bring in, just restate that, something from loop quantum gravity, so this idea of discreteness, right? Introducing all your surfaces and cuts in spacetime, and this idea of holography, of boundaries being important. Is that the thing? Like, what really you bring from loop quantum gravity?
Okay, so I'm not saying that I bring some things from holography and from. I'm saying that by looking at this system and just following what the system tells me, I can now recognize both elements, which is very different. I'm not trying to prove that one is correct or the other. I'm just looking at the system and finding it. So what you have is that now you have this corner sphere, and then you look at representation of this corner sphere, and okay, when you have symmetries, something which are very nice is to classify what we call the Casimirs, which are the objects which are invariant. Okay, I mean, it's a technical, but there's the techniques where you recognize the objects which, when you make the rotation, nothing changes, and these objects are central. They organize the system. I mean. I can give an example. This is the notion of symmetry, for instance, is why we can predict the weather system, right? So, and in fact, when we discovered the symmetry group of quantum gravity at the corner is extremely similar to the symmetry group that governs the meteorological weather system on the planet Earth.
Wow.
Okay.
Okay.
I mean, it's a mathematical equivalence, and anyway, it's a sidetrack. So we know that the weather system is chaotic and it's very complicated, but it's governed by a fundamental symmetry, and the fundamental symmetry has invariants, Casimirs, which are called which are the number and the locations of the vortices. And so if you have ever done some sailings, and back in the day where there was no computer, you could predict the weather for a few days, because what you would do is look at a map, locate the vortices, understand their speed, and know that for the next 3 days, before the vortex merge, nothing will happen in your track. Okay, and the vortices, why don't they move very fast? Because they are Casimirs. That is, they are protected by that symmetry. Okay, that's okay. So it's just to tell you how. Okay, and the same. Okay, the same kind of objects appear in this representation. So I'm trying to be okay. I got carried away, but because it opens up new. That's the one thing, we're studying this quantum gravity system, and then at some point we had to study the representation theory that meteorologists or mathematical physicists develop, because it's useful. This is the beauty of theoretical physics. At some point, there's
that's the importance of cross-contamination between different
cross-contamination,
right?
Yeah. So where does the quantum gravity idea comes in is that you look at these Casimirs, and one of these Casimirs is somehow the area element here. And then, you look at representation, and it's possible for this area element to be atomic. So then you can find image. If you think about this fluid on the corner as a fluid for a moment, a gravitational fluid, it could be made of atoms. And if it's made of atoms, then the spectral area is quantized. And it comes purely from representation theory.
Okay.
Now, so that's where I say, you look at the system, there's no discretization whatsoever, okay? You just look at representation theory, and boom, you find one option is this one.
Something which really resembles what happens in loop quantum gravity, in a sense. You have this.
Yes. Something that resembles exactly one of the key results of loop quantum gravity, but somehow with a little bit more symmetry. Like loop quantum gravity had to assume some pre-established edge, whereas here you have more flexibility somehow. Like you don't need to break some different invariants if you want.
Okay.
And maybe to conclude, how does it relate to holography? One of the central aspect of holography has been the emphasis. It's a link between, let's say, holography and quantum information. It's been the focus that somehow what we need to understand in quantum field theory is the entanglement entropy. That is, the idea that maybe geometry, at the quantum level is by definition the number of information shared across that entangling surface, right? Yes. And that's the way you should understand quantum geometry. You should not necessarily understand it as quantum geometry, as I just described, but you should understand it as purely informationally.
Yes, some kind of object that emerges from quantum entanglement, or which is made in some sense at the fundamental level.
Exactly. That geometry is the expression of quantum entanglement. And here, that's one aspect of what we have, because this symmetry group, it appears exactly when you have a link of entanglement between the two, and you cut it in half, and you realize that the half that you have on the left, in fact, carry a representation of symmetry. So you find that the symmetry controls completely the nature of quantum entanglement. Okay, so that's where we are. And anyway, so this is why I find it beautiful. And yeah, that's and it's just the beginning. And you see, you can you can bring different approach. One that I didn't mention, and I find fascinating in the past few years, I connected a lot with what's called celestial holography.
Yes.
Which is also some kind of bottom-up approach for scattering process, and it's very naturally linked. Yeah, I don't have time to explain, but if you take a sphere, I was talking about a small sphere, but if you take a big sphere and you move it along your null infinity, then anyway, you can see that we're talking about the same thing there. So that's another aspect where I would say we have loop gravity, holography, and celestial holography now in the same ground, and it's a much bigger playground than it was 5 years ago.
Well, this is absolutely remarkable, the way in which area quantization, but also this interplay between geometry and entanglement entropy comes in naturally. It's really fascinating. I mean, I'm excited. You see it on my face. So, but so I will. At this point, I was expecting to ask you what you think is the right approach to quantum gravity to solve the problem, but I guess you already answered the question. You put us in front of a nice bottom-up approach to the problem, which starts from symmetries and then tries to exploit them, read them off and exploit them to quantize the theory. And this is super interesting, and I thank you very much for your explanation. If I may, I would like to move towards the end of our conversation with just a brief personal question, because we are approaching 1 hour, right? We are about the hour, so I guess it's time for us to move towards the last question. Why did you choose quantum gravity in the first? Did you choose quantum gravity in the first place? I mean, you partially answered, but is there one single line answer to this question? This can be really helpful for students listening to us.
Yeah, I think there's a single line answer, and I remember exactly the moment it happened. I mean, the single line is just because it's the most fascinating, and it's the hardest problem in physics, in my view. And I remember the moment is that I started my PhD doing things, integrable systems, TQFT, they were interesting. But at some point, the world is a big space. I could become a doctor, I could become a banker, I could become an explorer. I love mountains. And I wanted to become a writer. I mean, there's so many things. I wanted a musician, so many things. And then I'm like, why am I doing physics? I'm doing physics because, I realized at one point in my PhD, I'm doing physics because I wanted to do these things, which are fascinating, but I was realizing that I was afraid they were not worthy of me in some sense, right? Like I say, no, I have to do realistic physics, right? Physics that, pay, I don't know, the rent or whatever. And then I decided, well, if I want to pay the rent, I go in this world and I can find any job I want, because that's true for any theoretical physicist. And I said, well, if I stay in this world, it's to do the thing that I'm really passionate about. It's to understand what is the atom of quantum geometry. And I realized that's only if it, even if it's just to decide I'm going to fail. But yeah, that's the...
Well, and with this, I think that I can thank you. This is really important. I will keep it with me. Thank you very much for your time. This was really valuable. And I'm sure it will be for the people that will listen to us in the near future, because this will be uploaded. And I want to, I don't know, advert everyone that many other conversations will come. And thank you again for your...
Thank you for organizing that. I think it's a great initiative.
Thank you. Thank you very much.
Thank you, Davide.